In this video, we'll discuss about feature extraction in NLP or natural language processing. So, why feature extraction is important in natural language processing? Computers just understand numbers and they cannot process raw text directly. Feature extraction converts the raw text into numerical form. So, it acts as a bridge between our human language and the algorithms. The quality of features directly impacts the model performance. So, without effective feature extractions, NLP models struggle to learn meaningful patterns. Good feature representations help improve accuracy, it reduces noise and captures semantic meaning or basically the meaning of the text. So, better feature extraction means the models will have better understanding of the text. Now, there are many traditional NLP feature extraction techniques. We'll discuss those. We'll try to understand the basic idea there. One-hot encoding, bag of words, n-grams, and TF-IDF. These are the main ones. We'll then see the transition into deep learning based NLP feature extraction techniques. So the first one is one-hot encoding. It represents every word as a n-dimensional vector. So it's basically for the word. How do we represent one word? N-dimensional vector means n is the size of the vocabulary. So in the vocabulary, every word has one position associated with it, starting from 1 to n, right? So in the n size vector, let's say this one or this one, only in the place of that position will have 1. Rest will be zeros. So this will give some unique representation for every word. So let's say if the aardvark or abacus, these are the first and second words in the vocabulary, and this one I can't even pronounce it. So this is, let's say, the last word in the vocabulary. So their one-hot vector representation will be something like this. So the first one, in the first position will have 1, rest 0. For the second word, in the second position will have 1, rest 0. And for the last one, in the last position we have 1, rest 0. So the one-hot encoding, this has lots of advantages, like it's very simple and intuitive. It gives some unique vector representation for each word. It works well for small data sets and it's as a starting point for NLP models. So it's useful as a baseline to build more advanced feature extraction techniques. So there are few limitations also there for one-hot encoding, like very high dimensional vectors. So the dimension is basically equal to the size of the vocabulary, and vocabulary size will be very large, right? So the vector size, vector dimension also will be very high. So extremely sparse with only a single one and rest are 0. So the vectors are sparse vectors. No context awareness. Each word is treated independently of others. So let's say the phrase the New York has a specific meaning, right? But one-hot encoding represents new and work as unrelated words. No semantic similarity. So what vectors of related words are not close to each other in vector space? So let's take example here like apple and orange. These two words, apple and orange, both are fruits, right? So they are somehow related. But if we try to measure the similarity between these two, apple and orange, so we can calculate cosine similarity. Cosine similarity is one way to calculate the similarity between two vectors. So let's say V apple is the one-hot vector for apple, V orange is the one-hot vector for orange. So the cosine similarity can be calculated with this formula. V apple transpose times V orange divided by norm of apple times norm of orange. So even though both are fruits, you see that this will give 0 because this one-hot vectors, these are orthogonal. So the dot product will give 0. So we are not able to extract any similarity from these vectors. Next is bag of words. So one-hot encoding was for a particular word. Bag of words is basically for a document or text. So it represents text based on word frequency. So we are given some long sentence in a document or text. It ignores the word order, grammar or sentence structure. It treats text as a bag of words, as a collection of words. If you give one sentence or one full document, it will just take the words and it will be a collection of words. It will treat it as a collection of words. So let's understand this with examples. So let's say these two documents I have. The first one is this sentence, the cat and the dog are friendly animals. So I'm just considering three words here for simplicity because I want to visualize this also, and beyond 3 dimension it's difficult to visualize also, right? So I have taken a cat, dog and animals. So what counts? Cat occurred only one times, dog occurs only one times, animals occurred only one times. So the vector here will be 1, 1, 1. So document 2 is the cat chased another cat while a dog watched. So the word counts, cat here occurred 2 times. Dog occurred only 1 times. Animals, there is no animals, so 0 times. So the vector will be 2, 1, 0. So let's try to visualize this in 3 dimensions because I have considered only 3 dimensions. So for the first document, the vector was 1, 1, 1. So let's say cat in this direction, dog in this direction and animals in this direction. So 1, 1, 1 will be 1 here, then 1 here, then 1 in this direction. So in this point. So this point 1, 1, 1, this will represent the cat and the dog are friendly animals, the first document. For the second one, the vector is 2, 1, 0. So 2 cats, right? 1 dog and 0 animals. So this will represent the second document. So this is how a bag of words represents text. Now bag of words can be represented as a weighted summation of one-hot encoding vectors in the document. It's basically we are just trying to come up with some formula to use. So let's consider the document D has T words like W1, W2 till WT. So one-hot vector representation for word WY is, let's say, VI. So bag of words representations of the document D. So let's say VD, this is the bag of words representation. It will be summation of all alpha I VIs. VIs are the one-hot vector representations and alpha I is some coefficient. What is it? So here the weights alpha i's can be the frequency of the words in the document. So how many times those the words occurred in the document. So these are the one-hot vector and these are the this many times this word occurred in the document. So let's understand this with the example also. So for this document, like the cat chased another cat while a dog watched, these are the word counts you already have seen, and these are the one-hot vector representation for cat, dog and animals, right? Only for the first position 1 for cat, second position 1 for dog and last position 1 for animals. We are just considering 3-dimensional for visualization. So the bag of words representation for the document will be 2 times vcat plus 1 times vdog plus 0 times vanimal. So we get 2, 1, 0, the same vector. So this is just how you perceive this bag of words. So what are the advantages and limitations of bag of words? So first of all, it's very simple, fast and effective for small data sets. Limitations like it ignores the word order. Like if you take the bag of words representation for cat eats fish. So in all of this, let's say all this word occurred only one times, right? So only in the places of cat eats and fish will have one, rest will be zero. It will be the same as the back and forth representation for fish eats cat, right? Only in the places of fish eats cat, like we'll have ones, rest will be zero. So the back and forth representation for both of this will be same because it's ignoring the word order. It's high dimensional, yet the one-hot vector representation is basically high dimensional, so this is also high dimensional. Sparse representation, so of course there will be lots of zero in the vector. Next technique is the n-grams. So in addition to the vocabulary, we can take bigrams like 2 words at a time, or trigrams like 3 words at a time. Also, you can take n-grams, basically n words at a time. So unigram, let's say only dip. Bigram, if you take, it will be like deep learning 2 words at a time. Trigram, basically deep learning models, 3 words at a time we are taking. So like in the sentence of cat eats fish, we can take the bigrams cat eats and eats fish, or we can take trigram like cat eats fish together. So these two sentences, cat eats fish and fish eats cat, won't be represented by the same vector as their bigrams and trigrams will be different. So it's kind of solves the problem, but it will have other limitations. So it preserves the local context, improves performance for some tasks, but the thing is vocabulary size explodes. Earlier also vocabulary size was huge, but again we added bigrams, trigrams, n-grams, let's say. So vocabulary size will explode. But still there is no semantic meaning. We're just taking those like words next to each other, right? We are not collecting any semantic meaning. So the next traditional feature extraction techniques in NLP is TF-IDF. So it's also very popular for NLP tasks. So it assigns importance to words. So frequency of a word in a document that it collects as TF, or term frequency. Term is basically the word here. Rarity across the corpus. So we are considering a collection of documents. The corpus is the collection of documents. So that is basically inverse document frequency. So it is basically a statistical measure to use to evaluate the importance of a word in a document relative to a collection of documents. So the word is basically referred as a term here. So first understand what is term frequency. Term frequency for a term T in the document D is basically defines the importance of term T in the document T. It's basically how many times this term or this word occurred in the document T. So count of term T in the document T divided by count of all terms in the document. So it's basically trying to find out in one document how many times this particular word or term occurred relative to other terms, because that's why we are dividing by count of all terms in the document D. Next is inverse document frequency, or IDF. So let's say our corpus has 10,000 documents and 100 of the documents contain term T. So the DF, or document frequency of term T, is 100 because it occurred in 100 documents. So the more number of documents contains the term, the more common it is. Like the term D, so that will be present in almost all the documents, almost all the 10,000 documents, right? So it should not be given that much importance. So that's why we're calculating the inverse document frequency. So what it is, it's total number of documents in the corpus divided by number of documents containing the term T, and we are taking the log of that. So we are dividing total number of documents divided by number of documents containing the term T. So in this case it will be 10,000 10 divided by 100 and log of that, log of 100. So we calculated term frequency, we calculated inverse document frequency. Term frequency is basically the frequency of a word in a document, and inverse document frequency is how rare this word across the corpus. And then we are multiplying this TF and IDF, and we are getting this TF-IDF representation for a word or term. Now, limitations of this traditional features. So, this treats words independently, and the representations, these are high dimensional mostly. So, they doesn't capture semantic meaning, and they cannot handle polysemies. Polysemies is the coexistence of many possible meanings for a word or phrase. So, let's say bank of a river and bank account. In these two sentences, bank means different, right? So this is bank of a river, and this is some financial institution, bank account, right? So, but in all of this traditional feature extraction techniques we saw, when both of them, bank will have the same representation. So now we'll see the motivation for better deep learning based feature extraction techniques. So what do you want basically? So in earlier we are having high dimensional vectors, and the vectors were very sparse and they are not capturing the meaning of the word, right? So what if we have a low dimensional, dense and meaningful vector representation? So that's what we are: dense vectors, low dimensional representations, and meaningfulness and semantic similarity between the vectors. Like similar words should be close in the vector space. So like this. So the cat, this is some dense low dimensional vector representations. How meaningful it is, I cannot say. We'll see now. So if these vectors are meaningful, we'll be able to do vector calculations with such vectors, right? So VW, let's say this is the vector representation for W, right? So V king minus V man plus V woman will get V queen. So this is some gender relationships we'll be able to capture if the vectors are meaningful. V walking minus V walk plus V run will get V running. So that is some tense relationships we can capture. V Delhi minus V India plus V France, we get V Paris. So it's some geographical relationships it is capturing. V cats minus V cat plus V dog, we get V dogs. Some pluralization. So I'm just giving few examples to understand like this type of meaning we want to capture in this vector. So let's say in this 2D 2 dimension, we are having the vectors of king, queen, man, woman, right? So we see king and queen are very closer, man and woman also very closer. So queen can be king minus man plus woman. So this type of calculation will be able to do with such vectors. So what are these vectors values, right? We just told it can be some dense vectors, low dimensional, but what are these values? So let's say these are some attributes like power, like king will have power, queen will have power. Man and woman, like normal general, in general, they will not have that much power. King, queen, they will be much richer, right, than normal people. Nothing is related to technology here. Gender, let's say I am taking -1 for male and 1 for the female, so it's -1, 1, -1, 1. So these are some attributes that comes to our human mind. So the vectors we'll be generating using deep learning might not have similar features, but we don't know what type of features deep learning models will learn, but it will try to understand, it will try to find out vectors in such a way that the vector calculations that we showed, right, that will be able to perform, or similar word vectors will be closer in the vector space. So here we have shown the vector calculation. So let's say king, this is the king vector, this is the man vector, and this is the woman vector. So king minus man plus woman, we get this vector, and this is the actual queen vector. So this can be close to each other, like it's very approximate. So now how do we get such low dimensional, dense and meaningful vectors? So we start with word to vec. So it learns dense vectors representations using deep learning where semantically similar words are closer in vector space. The key ideas here, words with similar contexts will have similar embeddings or numerical values. So similar words tend to occur together and will have similar context. These are the assumptions, and based on that it will do its whatever algorithm or techniques it will apply. So here the term similar we have used, right? So similar doesn't mean two words need to be synonymous, right? So, but it can mean like they can be related. Now let's try to understand with example. Let's consider this example here. The quick brown fox jumped over the lazy dog. So here, let's say we have taken one center word fox, this one. This is shown in red. And its context words for different window size is shown in blue. So context words means basically based on the window size. So here window size is 0. The fox doesn't have any context words. Context words means neighbor words, you can say. Here window size is 1. So we have this brown and jumped. These are the context words. Here in window size is 2. So we see quick brown jumped over. These 4 are context words. So the number of words in the context on the left side is equal to the number of words on the right side. Now there are two main models that we use to train. As a result of that, we'll get our word embeddings. Embeddings is basically the word vectors we are talking about. So the first one is skip-gram model. It predicts context words within a certain range before and after the current center word in the same sentence. And then continuous bag of words model or BoW model. It predicts the center word based on surrounding context word. So the context consists of a few words before and after the center word that we already discussed. So skip-gram model, let's say this word we have given, this is the one-hot vector representation of a word, and that is WT. This is the embedding layer we have, and embedding layer we have multiple nodes. All the layers will have multiple nodes. I have just shown as a block. What it will output? It will output the context word. So let's say if the window size is 2 here, right? So for WT, we'll have WT minus 1, WT minus 2, WT plus 1 and WT plus 2. This 4 context words, right? That will be predicting. BoW model, here we have given the context words. We have to find out the center word. WT minus 1, WT minus 2, WT plus 1, WT plus 2. All these are given. And we are trying to find out WT, the centered words. Now, in both this model, so predicting context words or center words, this is a fake problem we are trying to solve here. Our target is to get some word embedding or basically the word vectors, right? But we try to train this fake problems because we already have the data set where we know that context words and the center words. We try to train based on that, and we like as a result of this we'll get our word embeddings from this embedding layers. Next is GLOW for global vectors. It combines global corpus statistics with local context to produce staple embeddings. The key intuition here is the meaning of a word can be derived from how often it co-occurs with other words in the entire corpus. BoW builds a word-to-word co-occurrence matrix where each entry represents how frequently two words appear together within a fixed context window. So, for a sentence, we are taking one context window and we are taking the words and we are building a word-to-word co-occurrence matrix. And from that matrix, BoW learns word vectors such that the relationships between words are captured. Now, benefits and the limitations of this word embeddings that we saw that we use in word-to-vec or BoW approach. The benefits is we get dense vectors, semantic similarity of vectors. The similar words are close in the vector space. Better generalization we are getting, but the limitations is one vector per word and no context awareness. Like word bank will have same vector for river bank and bank word count. In both of the first phrases, bank will have the same word vector. Next we have contextual embeddings. So this Elmo, BERT, these models, they handle the context as well. So here it generates different vectors for same words based on context. So consider the word bank. So she deposited money in the bank. So here bank is basically a financial institution. He sat on the bank of the river. Here the bank is a geographical location. So this type of context-aware embedding models, this can have different word vectors for in different context. So it analyzes the entire sentence and captures syntax, semantics and long-range dependencies. So in the earlier methods we saw, we are having a context window and in those context window we are trying to find out the meaning, trying to find out the relationships. But here we are analyzing the entire sentences and we are trying to find the syntax, semantics and long range dependencies in the whole sentence. So that's why they are able to capture the context of a particular word. Next, transformer based feature extraction. So modern contextual embeddings are built using the transformer architecture. So this is the main architecture, main technique we use in today's time to extract features from the text data, which relies on self-attention. Well, I'll not go deep into this because I'll have a separate NLP session. There I will discuss more about this transformer architecture and self-attention, but I'm just trying to give some clue how it works. Self-attention allows each word in a sentence to compare itself with every other word. So if in a sentence we have multiple words, right? So consider any word. It will try to compare itself with all the other words. It will determine which words are the most relevant for its meaning. For each word, it will try to capture which other words are most relevant for its meaning. It weights information dynamically based on the context. And as a result, a word's representation is influenced by the entire sentence, not just nearby words. It's not based on a particular window, right? So it will consider the whole sentence. So the sentence can be big, right? So it will not just consider this window, it will consider all the words in the sentence, the full sentence it will consider. So that's why it will have a more informational expression for the vector. So why transformers dominate NLP? The transformers dominate NLP or natural language processing these days because they combine expressive powers with scalability. So it can express the meaning of the text much better and scalable. The computer transformer architecture, if you see, when I'll discuss later, I will discuss in detail, but it's very its expressive power and its scalability. These are the two main things. That's why transformers is dominating the NLP feature extraction. It is automatic feature extraction. Features are learned directly from the data, removing the need for manual feature extra engineering, and deeply contextual representations. Each word embedding adapts to sentence level meaning. Strong modeling of global dependencies. Long-range relationships are captured efficiently through attention. State-of-the-art performance. So transformers achieve top results across tasks such as translation, summarization, question answering, and text classification, and so on. So this is the gist of feature extraction in NLP. I'll discuss in detail in my NLP discussion.